Roughly 3,700 light-years from Earth, there's a planet orbiting the corpse of a dead star, and it completes an entire year in less than 8 hours. Its atmosphere is dominated by carbon, a chemical signature unlike anything found on any other planet ever confirmed, with barely a trace of hydrogen, the single most common element in the entire universe, the element that should, by every reasonable expectation, dominate the atmosphere of a planet this size. Gravity from its dead star companion is so extreme that the planet itself has been physically stretched into the shape of a lemon. And when a team of astronomers, using the James Webb Space Telescope, finished analyzing exactly what they were looking at, they came to a conclusion that doesn't happen often in a field built on careful, cautious, hedge-everything scientific language. No known theory currently explains how a planet like this could actually exist. This is the real story of PSR J2322650b, the strangest, most genuinely inexplicable planet. Astronomers have ever confirmed, and why NASA's own scientists are describing it as a discovery that's actively rewriting the rules of what a planet is even allowed to be. I'm your host, and this is your channel. If you want the real science behind the biggest discoveries in space, subscribe now, because we're just getting started. To understand why this specific planet has generated this level of genuine scientific bewilderment, you first have to understand exactly what kind of star it's orbiting, because that star is every bit as strange as the planet itself. PSR J2322650 is a pulsar, and pulsars are already among the most physically extreme objects known to exist anywhere in the universe. When a massive star reaches the end of its life and explodes as a supernova, its outer layers are blasted away into space, but its core, if it isn't massive enough to collapse all the way into a black hole, can instead collapse into something called a neutron star, an object so dense that a single teaspoon of its material would weigh roughly 1 billion tons here on Earth. A neutron star typically measures only about 12 miles across, roughly the size of a city, yet packs in more mass than our entire sun. Some neutron stars, formed under just the right conditions, end up spinning at astonishing speeds, in some cases hundreds of times per second, and as they spin, they sweep beams of radiation out into space from their magnetic poles, beams that, from Earth's specific vantage point, appear to pulse on and off with metronomic, almost impossibly precise regularity, similar to the beam from a lighthouse sweeping past a distant ship. Astronomers call these specific objects pulsars, and PSR J2322650 is one of them, a rapidly spinning stellar corpse, the compressed, superdense remnant of whatever star existed in this location before it exploded, likely billions of years ago. Finding any planet at all orbiting a pulsar is already a genuinely rare and remarkable event in the history of astronomy. The very first exoplanets ever confirmed anywhere in the universe, back in 1992, were actually found orbiting a different pulsar entirely, discovered by radio astronomer Alexander Volstran, a landmark moment that predates the discovery of the first planet orbiting a normal, sun-like star by several years. Pulsar planets remain, even today, a genuinely unusual category of object, and for good reason. The supernova explosion that creates a pulsar in the first place is an almost unimaginably violent event, one that should, under most circumstances, either destroy any planets that happened to be orbiting the star before it died, or fling them out of the system entirely through the sudden, dramatic loss of the star's mass and the accompanying blast wave. Any planet found orbiting a pulsar today is either a genuine survivor of that violence, having somehow endured the star's death, or, in some documented cases, an object that formed afterward, condensing out of the debris and leftover material still swirling around the newly formed pulsar following the supernova itself. PSR J2322650b, the specific planet at the center of this story, falls into an even more extreme category within that already rare group. Its mass is comparable to Jupiter, the largest planet in our own solar system, but its orbit is astonishingly, almost impossibly tight. It completes a full orbit around its pulsar host in under 8 hours, meaning it sits extraordinarily close to an object whose gravity and radiation environment are already among the most extreme found anywhere in the observable universe. For comparison, Mercury, the innermost planet in our own solar system, takes roughly 88 days to complete a single orbit around the Sun. This planet completes multiple orbits in the time it takes you to sleep through a single night. That extreme proximity to its dead star host is precisely what produces the planet's most visually striking and scientifically significant physical distortion. NASA's own description of the discovery lays out the mechanism directly. Gravitational forces from the much heavier pulsar are pulling the Jupiter mass world into a bizarre lemon shape. This isn't artistic embellishment or a loose approximation. It's a real physical consequence of orbiting this close to an object, this massive and this dense. Gravity doesn't pull on every part of an orbiting body with exactly equal strength. The side of the planet facing its host star experiences a measurably stronger gravitational pull than the side facing away, a phenomenon astronomers call tidal force, the same basic physics responsible for ocean tides here on Earth, caused by the moon's gravity pulling slightly harder on the near side of our planet than the far side. Around most planets and stars, this tidal effect is subtle, barely noticeable without careful, precise measurement. Around a pulsar with a planet orbiting this close and this fast, the effect becomes dramatic enough to visibly deform the entire shape of the planet itself, stretching it elongated along the axis pointing toward and away from its host, producing exactly the kind of tapered, asymmetrical silhouette that gives this planet its lemon-like profile. But the shape of the planet, as genuinely remarkable as it isn't actually the detail that has left astronomers describing this discovery as something current theory simply cannot explain. That distinction belongs to the planet's atmosphere. And to understand why, you need to understand what astronomers expected to find there in the first place, based on decades of prior research into how planets, and specifically giant Jupiter-mass planets, typically form. Every giant planet astronomers have studied in detail up to this point, whether inside our own solar system or orbiting other stars entirely, shares one overwhelmingly consistent chemical characteristic. Their atmospheres are dominated by hydrogen, typically alongside a meaningful quantity of helium. This isn't a coincidence or a minor detail. It's a direct, predictable consequence of how giant planets are believed to form in the first place, condensing out of the same vast disk of gas and dust that originally surrounded a young, still-forming star, a disk overwhelmingly composed of hydrogen and helium, the two lightest and by far the most abundant elements in the entire universe, produced in enormous quantities during the earliest moments of the Big Bang itself. Jupiter, Saturn, and virtually every confirmed gas giant orbiting other stars carry the same basic hydrogen-dominated chemical signature, a consistent pattern that is held up across literally thousands of confirmed exoplanet observations gathered over the past 3 decades. When the research team pointed the James Webb Space Telescope's spectroscopic instruments toward PSR J2322650b, specifically designed to identify the precise chemical composition of a distant planet's atmosphere by analyzing exactly which wavelengths of light that atmosphere absorbs and emits, the results broke that established, decades-old pattern completely. Rather than the expected hydrogen-dominated signature found in every other confirmed gas giant, this planet's atmosphere turned out to be overwhelmingly dominated by carbon, with hydrogen reduced to barely a detectable trace, a genuine chemical inversion of what every prior giant planet observation had consistently shown. According to NASA's own description of the finding, the planet's carbon-rich atmosphere contains soot clouds and quite possibly diamonds forming deep within its interior, an atmospheric chemistry profile that simply has no confirmed precedent anywhere else in the entire catalog of studied planets. It's worth taking a moment to actually understand why a carbon-dominated, hydrogen-depleted atmosphere is so much more than a minor chemical curiosity, because the implications reach directly into fundamental questions about how planets form in the first place. If a planet forms the conventional way, condensing directly out of a young star's protoplanetary disk, its atmosphere should inherit that disk's overwhelmingly hydrogen-rich composition almost automatically, simply because there's so much more hydrogen available in that environment than any other element. Finding a Jupiter-mass planet with hydrogen reduced to a bare trace, replaced instead by an atmosphere dominated by carbon, suggests one of 2 genuinely dramatic possibilities. Either this specific planet didn't form through the conventional process at all, having instead assembled itself through some entirely different, currently unidentified mechanism specific to the violent, chemically unusual environment surrounding a pulsar, or it formed normally, and then, at some point afterward, lost the overwhelming majority of its original hydrogen atmosphere entirely, stripped away by some combination of the pulsar's intense radiation and its own extreme, punishing proximity to its dead star host, leaving behind only the heavier, more resistant carbon compounds that a hydrogen atmosphere would normally have diluted and outnumbered by an enormous margin. Neither of those 2 explanations currently has a fully worked out, confidently supported theoretical model behind it, and that absence is precisely what makes this discovery so genuinely significant, rather than simply another entry in an already long catalog of strange exoplanets. The research team's own conclusion, as reported by NASA and widely covered across the scientific press, states the situation with unusual directness for a field that typically favors careful, heavily qualified language. Scientists are stunned, and no known theory explains how such a planet could exist. That's not casual, informal commentary from an unrelated observer. That's the described reaction of the actual researchers who ran the analysis examined the data, checked it against every plausible existing model of planetary formation and atmospheric evolution, and came away without a satisfying explanation for what they'd actually found. It's worth being precise and careful about exactly what that specific admission does and does not mean scientifically, because getting this distinction right is the difference between honest, credible reporting and manufactured, exaggerated drama. It does not mean the laws of physics have been broken or that something impossible has literally occurred. Every individual physical process involved here, tidal deformation, atmospheric chemistry, pulsar radiation, obeys entirely conventional, well-understood physics on its own. What it does mean is that the specific combination of circumstances producing this particular planet's atmosphere doesn't fit cleanly into any of the existing theoretical frameworks astronomers currently use to explain how giant planets form and evolve. Somewhere in the violent history of this system, whether during the original supernova that created the pulsar, during the planet's initial formation, or across the billions of years since as the planet endured its host's relentless, extreme radiation environment, something happened that stripped away or fundamentally altered this planet's atmospheric chemistry in a way current models simply weren't built to anticipate or explain. This discovery arrived amid what has become a genuinely remarkable, sustained stretch of exoplanet research using the James Webb Space Telescope, and it's worth placing PSR J2322650b within that broader context, because the pace and variety of genuinely strange findings coming out of Webb's exoplanet program over the past couple of years has been substantial. In May 2026, a separate research team studying a different giant planet, located nearly 700 light-years from Earth, identified a genuinely bizarre daily weather pattern. Mineral clouds that form fresh every morning and completely vanish again by nightfall, an alien meteorological cycle with no equivalent anywhere in our own solar system, driven by the planet's extreme proximity to its own host star, and the resulting dramatic temperature swings between its permanently sun-facing and permanently dark hemispheres. A separate finding, reported in June 2025, identified an entirely different kind of impossibility. A giant planet, roughly the size of Saturn, discovered orbiting an exceptionally small, dim red dwarf star. That planet, designated TOI 6894b, immediately posed its own genuine theoretical puzzle because prevailing models of planet formation have generally predicted that small, low-mass stars like this one simply shouldn't retain enough raw material in their surrounding protoplanetary disk to build a planet this large in the first place. The scientists who identified TOI 68894b described their own reaction in terms that echo the PSR J2322650b findings directly. They had discovered a giant planet orbiting a star so small that current theory suggested this combination shouldn't be possible at all. And in July 2026, an entirely separate Webb research effort turned up yet another genuinely surprising result, this time within one of the most extensively studied planetary systems in the entire history of exoplanet. Astronomy. Astronomers examining Beta Pictoris, a young nearby star system already known to host 2 confirmed giant planets, one of which, Beta Pictoris b, was among the very first exoplanets ever directly imaged by any telescope, discovered an entirely new, previously undetected giant planet hiding within that same extensively studied system, found not through conventional direct imaging, but through an entirely different technique involving moderate resolution spectroscopy, catching a specific telltale chemical signature in the system's light that had simply gone unnoticed through years of prior, more conventional observation. Taken together, this pattern of discoveries reveals something genuinely important about the current state of exoplanet science, well beyond the specific details of any single strange planet. James Webb's extraordinary combination of sensitivity and spectroscopic precision is allowing astronomers, for the first time in the history of the field, to actually characterize the detailed physical and chemical properties of individual exoplanets, rather than simply confirming their existence and estimating rough physical parameters like mass and orbital period, the kind of basic information earlier generations of exoplanet hunting telescopes were largely limited to providing. That shift from detection to genuine characterization is precisely what's producing this steady, ongoing stream of discoveries that don't fit existing theoretical models. Astronomers aren't simply finding more planets. They're finally getting detailed enough information about the planets they've already found and the ones they continue discovering to notice exactly where and how those planets diverge from decades of careful theoretical prediction, revealing an underlying diversity in planetary formation and evolution that earlier, cruder observational techniques simply weren't capable of detecting at all. It's also worth situating PSR J2322650b within the broader historical catalog of genuinely strange exoplanets astronomers have identified over the past 3 decades, because doing so helps illustrate exactly how unusual this specific carbon atmosphere finding actually is, even against an already impressively strange field of competitors. Kepler 16b, discovered by NASA's Kepler Space Telescope and located roughly 200 light-years away in the constellation Lyra, orbits 2 separate stars simultaneously in a genuine binary star system, producing an orbital environment with 2 visible sunsets each day, a real-world planetary configuration. Frequently compared to the fictional planet Tatooine from the Star Wars films. TOI 849b, discovered by NASA's Transiting Exoplanet Survey satellite in 2020, orbits so tightly and so close to its host star that a complete year passes in just 18 hours, and despite being roughly Neptune-sized, it turns out to be dense and rocky rather than gaseous, making it the largest confirmed rocky world ever detected, and quite possibly the exposed surviving core of a former gas giant that had its entire outer atmosphere stripped away entirely by its host star's radiation, leaving only the dense, rocky core behind. TAC 2241 and 249530b holds one of the most extreme, elongated orbits ever recorded for any confirmed exoplanet. Even against this genuinely impressive lineup of previously confirmed cosmic oddities, PSR J2322650b stands out, specifically because of that combination of a hydrogen-depleted, carbon-dominated atmosphere paired with an actively documented lack of any working theoretical explanation for how it could have formed this way in the first place, a distinction that separates it from planets that are simply unusual in scale or orbital geometry, categories that, while genuinely strange, don't actually challenge the fundamental theoretical frameworks astronomers use to understand how planets form and evolve. It's also worth being clear and direct about one thing this discovery is not, because there has been genuine documented confusion online about unrelated exoplanet stories circulating around roughly the same period. In January 2026, a separate and completely unrelated claim spread across social media, alleging that a newly discovered exoplanet called TOI 1846b was emitting mysterious, unexplained signals, language that fact-checking organizations subsequently traced back to a misunderstanding, or in some cases, a deliberate mischaracterization of routine, well-understood transit data, the standard conventional method astronomers use to detect exoplanets by measuring the tiny, predictable dimming that occurs when a planet passes directly in front of its host star. That specific claim about mysterious signals was not accurate, and it has no connection whatsoever to the very real, very different, and considerably more rigorously documented findings surrounding PSR J2322650b's actual confirmed atmospheric chemistry. It's worth flagging that distinction directly, because the exoplanet research space has, over the past couple of years, produced both genuinely remarkable, documented discoveries like this pulsar planet, and separately, a fair amount of exaggerated or entirely fabricated online content dressed up to look similar, and telling the two apart requires checking whether a specific claim actually traces back to a named research team, a peer-reviewed publication, and an official NASA or university statement, exactly the kind of verification this particular pulsar planet discovery holds up to without difficulty. So what happens next with PSR J2322650b, now that this initial, genuinely puzzling data has been gathered and published? As is standard practice for any major, unresolved finding in astrophysics, the research team's own stated position is that, further, more detailed observation and continued theoretical modeling will be required before scientists can offer a confident, well-supported explanation for exactly how this planet ended up with the atmosphere it currently has. That might eventually involve additional Webb observations, gathering more detailed spectroscopic data across a broader range of wavelengths, searching for additional trace chemical signatures that could help narrow down the specific formation and evolutionary history responsible for producing this particular atmospheric composition. It might also involve entirely new theoretical modeling work, attempting to simulate, from first principles, exactly what happens to a planet's atmosphere when it's forced to endure the specific combination of extreme tidal forces, intense pulsar radiation, and unusual formation conditions that a world like PSR J2322650b has apparently experienced across its lifetime. Understanding this single strange planet in real detail could plausibly reveal an entirely new category of planetary formation and evolution, one specific to the genuinely extreme, violent environments surrounding pulsars. Environments dramatically different from the comparatively calm, stable conditions surrounding an ordinary, sun-like star that most existing planet formation theory has been built to explain. So here is where this genuinely, honestly stands, based entirely on NASA's own published statements and the direct findings of the research team responsible for this discovery. A Jupiter-mass planet orbiting a rapidly spinning city-sized neutron star just under 8 hours per orbit has been physically stretched into a lemon shape by extreme tidal forces in its atmosphere. When finally analyzed in detail using the James Webb Space Telescope's spectroscopic instruments, turned out to be dominated by carbon rather than the hydrogen. Every other confirmed giant planet in the known universe reliably displays, with soot clouds and possibly diamonds forming somewhere within its bizarre, unprecedented atmospheric structure. According to the researchers who actually made and confirmed this discovery, no existing theoretical model currently explains how a planet with this specific combination of properties could have formed or come to exist at all. That is not manufactured drama built around an exaggerated headline. That is the honest, direct, genuinely startling conclusion of real scientists, working with real, peer-reviewed data, confronting a planet that simply doesn't fit inside any box modern planetary science has built so far. If this kind of story is what you come here for, one grounded in exactly what NASA's own researchers actually measured and openly admitted they can't yet explain rather than exaggeration, hit subscribe and turn on notifications, because there's clearly an entire category of planetary formation still waiting to be understood at the edges of the strangest environments in our galaxy. Drop a comment telling me what theory you think will eventually explain this planet's bizarre carbon atmosphere, and share this with someone who still thinks astronomers have already found and cataloged every possible way a planet can exist.